today I just wanted to talk to you a little bit about, let me get this organized here. Okay. Why are we all here? I mean, basically, we need to really think about that and step back. We're all here because we either are someone designing a chip or we have a customer who needs a chip that needs to be designed for something that most likely fits into the Internet of Things, the word of the day. And what I'd like to do is just kind of walk through, eSilicon is a company that designs chips. We actually deliver packaged and tested chips. And we also have our own IP as well. So we have the ability to build optimized or customized IP. And I'd like to kind of work through from sort of the high level, what are the considerations that we have to be able to do our designs, and what is driving us to make the decisions that we're making. So if you think of the Internet of Things, right, it's been growing and growing and growing, and astronomically we're likely to see it growing much faster than it has been to date. And I want to show you a few examples of some chips that we've built that have actually started at the application side or the front end, where you're accessing this a large amount of data that's being collected. And then on the other side of things, where the network is trying to keep up with this large amount of data, we're going to have sensors virtually in everything, everywhere. And all of this data is going to have to be managed. And so we're going to have chips that's going to be able to keep up with that. And there's an astronomical amount of power that's going to be, out there trying to run these machines, and we need to be able to keep that down. So what is driving our customers that are building products in the Internet of Things? Well, first, they need to have the ability to have standardized software and hardware. They also need the ability to be able to build something that's cheap. And so to do that, of course, we have to say Moore's Law in this presentation as well. The onset of sensors and the collection of additional data as well is going to really put stress on the networking side of things. So from an ASIC perspective, what we are really seeing is a lot of necessity for low power. So when we look at low power and doing designs in low power, I picked a couple of them from 28 nanometer. These are real designs that we have done, and they're just some considerations as far as products and development. So if we look at the front end, at the application interface, for example, we all know we've got iPads, phones, etc. We're going to have mobile devices. This is a particular device that actually, when the customer came to us, they didn't even tell us what the product was. It was so secret. But 28 nanometer technology, this one is a relatively small design. It's around 16, 17 million devices or gates. And the memory subsystem is only 40 megabits. Now, the other example I'm going to show you is a much bigger one on the networking side. But this particular customer needed to have a very aggressive schedule. And they also needed to have the absolute lowest achievable idle and standby power. So when we looked at this design, there are a lot of IP providers out there that provide very good standard memory IP. This is an example of looking at a design and saying, okay, if we use what's off the shelf, here's where we're going to be. We're not going to meet what the customer requires. So what can we do about that? So if you look at this graph at the bottom of the chart, you can see that 90% of this particular design had one memory that contributed to 90% of the bits in this design. And so if we could take a look at that and use what's available on, and start with what's available, but then really figure out what we could do to optimize it. In this case, obviously dual voltage rails are out there where you're able to separate the periphery and the array and run with two different voltages to be able to lower the power. Periphery shutdown is available out there. But what if you want to look at different devices that are in your critical path of the memory? What if you want to trade off standard VT and ultra-high VT and really be able to optimize it? You don't really have a lot of options for that. And that's what we've done with this particular design. And we've just also we've looked at different bit cells, for example. I'll show you some more information about that in the next design, but really trading off a low leakage bit cell for a standard bit cell, which are not always available as standard products. So in this particular example, we had an 8x improvement in standby power and a 20x improvement in idle power by doing our optimization. Now, on the flip side, if we take a look at a networking example, a much bigger chip, still 28 nanometer, 130 million gates, over 400 megabits of SRAM, and of course, it has around 70 high-speed SerDes in this design. So this customer's target was 40 watts of power, and they wanted to run at 600 megahertz. Again, this is another example, an SRAM example. There was one particular memory that was replicated over 2,000 times. So it's a no-brainer that if you can optimize that one particular memory, you can make a significant difference. But that's not the only thing that we did. We also took a look at the architecture and elevated the redundancy to be able to move it up to a higher level since you had one block that was replicated so often. We also tweaked the ECC so it was just the right amount of ECC for this particular customer. And then it includes our ternary CAM that we built. Now, what we did that was a little bit further, again, we did similar things as in the prior example, where we were modifying the critical path. We were putting in some ultra-high VT devices in place of standard VT. We did the bit cell swap. But the thing is, we were able to get this answer very quickly. We have data analysis systems within our company that basically store all of the data and analyze all of the data across multiple foundries, across multiple technologies. And so we're able to get this data very quickly and give a response to our customer. So if we look at the analysis that was done, the further thing that we did is we asked our customer if they could actually reduce the frequency of their chip. Could they go down a little bit in frequency to trade that off for power? And then we also binned the parts, and we ran at 2 different voltages. And by doing this analysis and working with our customer, we were able to go from over 65 watts of power down to below 40 watts, which was their target. So yes, there was a little bit of give and take on that, but this is some additional methods to be able to reach the lower power that our customer was looking for. So at eSilicon, we build chips. We also have IP. We're happy to do customized IP for our customers. And we'd love to have you come visit us at booth 512. And we also have some demonstrations of some e-commerce products that we have available to be able to do MPW quotes and to be able to have memory analysis online. It's a little bit different than things that you have seen in the past. So